Assalamualaikum. Okay, so today we're in lesson 3 in chapter 2. Chapter 2 is about capacitors and dielectrics. So there is 3 parts to chapter 2. The first one is capacitors in series and parallel. The next one is charging and discharging of capacitor. And the last one is capacitors with dielectric. But before that, what is a capacitor? So a capacitor is actually a device that can store, it stores electric charge. It stores electric charge. A capacitor consists of 2 conducting plates. So we have 2 plates. This is the first one and the second one. And then it has separated by a small air or gap. So it can be in the center. In the center here, it could be air, or it can also be thin insulator. So some capacitors is separated by air, whereas some capacitors has dielectric at the gap. So this is examples of capacitor, and this is the symbol for capacitor, electrical symbol for capacitor. So we straight go into the first part. So the first learning outcome is you should be able to define and use the equation of capacitors. So define and use the equation for capacitance. So what is capacitance? Capacitance is the ability. Capacitor is the device, whereas capacitance is the ability of the capacitor. The ability of the capacitor to store charge. That means if a capacitor can store a lot of charge, the capacitance is higher. Whereas if a capacitor can only store a little bit of charge, we would say the capacitance of that capacitor is lower. And then next one, so this is the formula for capacitance. C equals to Q over V, where C is actually the capacitance. So C is the capacitance, Q is the charge, and V is the potential difference. C is the capacitance, Q is the charge, and V is the potential difference. And we know the unit for charge is coulomb, and the unit for potential difference is watt. So the unit for capacitance is actually farad. Farad. And then smaller, we can also use if you have a very small capacitance, so we will use a microfarad or nanofarad or picofarad. So those are for small values. Next, 1 farad of capacitance can charge either the plate is 1C when the potential difference across the capacitor is 1V. That means if we have 1 coulomb over 1 watt, we will get 1 farad. That's the first learning outcome. And the next one is you should be able to derive and determine effective capacitance of capacitors in series and also in parallel. As you have already known, if the capacitance is arranged side by side, side by side, we would say the capacitors are in series. Whereas if the capacitance is arranged above and below, we would say the capacitance are arranged in parallel. So for this case, the capacitors are arranged in series. And for us to understand how it works, first things first, we need to know if we have a circuit like this, the current will come out from the positive terminal. The current will flow like this. This is the direction of flow of current. Whereas the charge would flow in the opposite direction of current. So if current moves to the left, the charge will move to the right. So we have the charge. So the charge or the electrons would actually move towards the right. So this is the direction where the electron would move. So when the electrons move from the negative terminal out, the electrons would be collected here. So we would have a number of electrons here. Okay, so the pink ones are the electrons. These electrons on this plate here would actually repel the electrons from this plate. So it will repel. So when they repel, it will cause the electrons to flow this direction. So the electrons will flow in this direction. So when it repels, these electrons will move to the next plate. Okay, so the electrons will move into to the next plate here. And here would be positively charged because only protons are left. All electrons have been repelled. So only protons are left, and here would be negatively charged. And the process would repeat. Okay, and the process will repeat. Since here would be negatively charged, it will cause the other plate to have its electrons repelled. So when the electrons repel, the electrons will move this way. Okay, and here would be positively charged. And it repeats again. So the electrons would be collected here. Okay, the electrons will be collected here, and it will cause the electrons to repel, and here would be positive. There will be more protons there and less electrons. So all the electrons would travel in this direction. Okay, so hence it actually charges. If you could see the last sentence here, hence the charges on all three capacitors are the same. Okay, because it's the same charge on each capacitor which is moving. Okay, they are not divided into three. So it's the same charge which is moving. Okay, so if we read the sentence, when the circuit is completed, that means when the switch is closed, the electrons move away from the negative terminal of the battery here. Okay, to the one plate of C3. So the electrons gather here and repels the electrons from the other plate, okay, and causes this plate to be positively charged. Okay, so that's why our total capacitance, we would have a negative on this end and a positive on this end. It would be negatively charged this side and positively charged this side. Okay, so this is for capacitors connected in series. So all charges of three capacitors are the same. The most important concept is we should know when the electrons are collected here, it will repel the electrons on the other side of the plate, causing the electrons to move to the other plate and causing this plate to be positively charged. Okay, so our equation would be, our equation for just now would be, so we have already know C is actually equals to Q over V. So C equals to Q over V. And we know for C1, C2 and C3, they have the same charge. Okay, the charge are equal. Okay, so we start by equaling all the charge. So we know Q1 equals to Q2 equals to Q3 and equals to the total charge of the whole circuit. Whereas for the voltage, okay, for the voltage, the total voltage here would be V1 plus V2 plus V3. Okay, so to calculate the voltage, we would be V1 plus V2 plus V3. Okay, and then if we rearrange this equation, we would get V equals to Q over C. So we replace the potential difference here with Q over C. So Q over C equals to Q1 over C1 plus Q2 over C2 plus Q3 over C3. So we replace it. Okay, we use this equation to replace it. And finally, since we know all the charges are the same, we could actually divide it, or all the charges would cancel, and this would be our final equation to calculate the capacitance of the circuit. Okay, so this would be our equation. So this is for the series capacitors connected in series. So next, would be capacitors connected in parallel. Okay, capacitors connected in parallel. So for capacitors connected in parallel, the concept is still the same. So we know the current would flow this way. Okay, current would flow this way, and the electrons will always flow in the opposite direction of the current. So the electrons will actually flow this way. Okay, electrons will flow this way. And when you reach here, you can see it's actually splitted into three. So some electrons would be collected here, some electrons would be collected here, and some electrons would be collected here. So it's splitted into three, it's divided into three. Okay, and then the same thing will happen when the electrons are collected here. It would cause this plate to be negatively charged. Okay, so when this plate is negatively charged, it would repel. Okay, it will repel electrons on the opposite plate. Okay, so it will repel electrons on the opposite plate. So when it repels electrons, the electrons will flow out in the opposite direction of the current and back into here. Okay, so that's how it flows. Okay, but what we want to talk about this time is we want to talk about the capacitance when we connect the capacitor in parallel. Okay, so when it's connected in parallel, since the battery or the power supply is here, so the voltage for each point, whether it's here, here, or here, the voltage for each capacitor will actually be equal. Okay, the voltage for each capacitor would be equal. And this time, when the capacitance is equal, but actually the charge need to be added up. So to calculate the total electrons, we need to add up all the charges since it splits here into three parts. So the total charge needed to be added up. So we add Q1, Q2, and Q3. Again, we know the equation C equals to Q over V. Okay, therefore Q equals to CV. Okay, and then we substitute it into this equation. So we get Q equals to Q1 would be replaced with C1 and V1. Q2 would be replaced with C2 and V2. Q3 would be replaced with C3 and V3. And since all potential difference are equal, it can actually be divided or cancelled off, because each capacitor has the same potential difference since it's connected in parallel. Okay, because the capacitors are connected in parallel, it has the same potential difference, so it can be cancelled. And this would be our equation to calculate capacitors in parallel. Okay, when the capacitors are connected in parallel, we just add up each capacitors to get the total capacitance. Okay, so that's for capacitors connected in parallel. And the last part, we talk about energy stored in capacitors. So we've already known capacitors actually stores electrical energy. Okay, so when they store charge, it's actually storing electrical energy. Okay, so energy stored in a capacitor would be equal. Okay, how much energy stored in the capacitor would be equal to the work done to charge it. Okay, so that means if we put more work into charging the capacitor, the energy would be bigger. That's what it means. Okay, so energy stored in the capacitor will actually be equal to the work done to charge it. Okay, and we know the capacitor does not charge instantly. It takes time. The electrons need to flow and then it gets charged. Okay, so it takes time. So we will talk about how the capacitor charge later on in the next part. But before that, we need to calculate the work done to calculate the work needed to store a total charge of Q. Okay, so we would start with dW, okay, which is rate of change of work. Rate of work equals to V dQ. Okay, the change of work, this is dW. So the change of work will be equal to the change of charge. Okay, and then we integrate. So when we integrate it, again, we have V here. And then we have the equation where C equals to Q over V. Okay, C equals to Q over V. So when we rearrange, V would actually equal to Q over C. Okay, V equals to Q over C. So we will replace the V here with Q over C. So that's why we get the next part of that's how we get the following part of the working. Okay, so we replace it with Q over C. And then we integrate it from 0 until Q. And since C is the capacitance, okay, so the capacitance is actually a constant. For this integral, the capacitance is actually a constant. So we can remove it. So we left with Q dQ. And when we integrate it, it will become Q squared over 2. And since we are integrating it from 0 to Q, so this would be our final work done equation. This one. Okay, this would be our final work done equation. So that would be the first equation to calculate energy stored in the capacitor. Okay, so we want to calculate the energy, but we know the energy is actually equal from this part. We want to calculate the energy, but we know the energy is actually equal to the work done to charge it. So when we got the work done here, we actually got the energy. Okay, but there's another two equation. When we rearrange, we can actually get the other two equation. So for this equation, it starts from the earlier equation. So it starts from U equals to 1 over 2 Q squared over C. Okay, it starts from that equation. And since we've already known C equals to Q over V, so we rearrange it. Okay, if we rearrange it, we will get Q squared equals to C squared V squared. Okay, Q squared equals to C squared V squared. When we rearrange this equation we rearrange and we square. Since we have Q squared now and we square it, we will get Q squared equals to C squared multiplied by V squared. And then we substitute it into the equation. So we know Q squared is actually C squared multiplied by V squared over C. And then this capacitance C would cut the power 2, and we would be left with U equals to 1 over 2 C V squared. Okay, so this is another equation for energy stored in the capacitors. Okay, and the final equation, the final equation starts from the second equation. So we will use the U equals to 1 over 2 C V squared. So it starts from this equation, and then again we know C equals to Q over V. Okay, so C equals to Q over V. So we replace the C here with Q over V. So U equals to 1 over 2. Okay, and then the C would be replaced with Q over V squared. Okay, so this potential difference will cancel with this to the power of 2, and our final equation would be U equals to 1 over 2 QV. So that's how we have 3 equations. So this is the first one which we have integrate. The second one, okay, so we will use the first equation and we will use the capacitance equation, rearrange it, and we will get the second equation. And the third one, we will use we will start from the second equation, rearrange it, and we will get the third equation. Okay, so when we rearrange, we will always be using C equals to QV again. So we have three equations to derive and use energy stored in a capacitor. Okay, so that's all for 2.1. So next we will go to 2.2. Okay, next we continue with 2.2, which is charging and discharging of capacitors. Okay, since we've already known, a capacitor can store electric charge. Okay, a capacitor stores electric charge. Therefore, there will be the process where we charge. That means we provide the charges, and then the capacitor would actually store the electric charge. Okay, and there will also be a process where we discharge, where the charges are removed from the capacitor. Okay, so that is charging and discharging of capacitors. Okay, for this part, the first learning outcome is state the physical meaning of time constant and use the equation tau equals to RC. Okay, so what is time constant? Okay, time constant is a measure of how quickly the capacitor charges and discharges. Okay, so time constant is a time to measure how quickly a capacitor charges and discharges. Okay, so the physical meaning, you also know this equation where tau equals to RC. Okay, where tau is time constant, R is resistance, and C is capacitance. Okay, tau is time constant, R is resistance, and C is capacitance. So if we want to calculate how quickly a capacitor can actually charge or discharge, okay, so we can take its resistance, multiply by its capacitance. So we will get the time constant. And from the name itself, it says time constant. So definitely it will have a unit of seconds. Okay, so the unit for time constant is seconds, and it has the equation of tau equals to RC, and time constant is to measure how quickly a capacitor charges or discharges. Okay, so that's the first part. The next part is where the next learning outcome. Okay, the next learning outcome is where you should be able to sketch and explain the characteristics of QT and IT graph. Okay, so QT is actually charge against time graph, and IT is currents against time graph. Okay, for charging and discharging a capacitor. Okay, so that means, so for example, we have a circuit here. Okay, this circuit we will actually call it a RC circuit. Okay, this is a RC circuit. That means it has a resistor and it also has a capacitor. Okay, resistor, capacitor. So RC circuit. Okay, and like I've said earlier, when we have a circuit like this, the current will always flow out from the positive terminal of the battery. Okay, so the current will flow this way, and the charge or the electrons will always move in the opposite direction. Okay, so we have the current going in here and the charge moving in the other direction, which is the blue arrow. Okay, so what happens is, this is where we say when the switch S is closed, okay, the current immediately begins flowing out. So the current flows out from the positive terminal. Okay, and when the current flows out from the positive terminal, at the same time, the electrons will move out from the negative terminal. Okay, the electrons will move out from the negative terminal. And when the electrons move, the electrons will actually accumulate. Okay, the electrons will accumulate here. So we will have more electrons here because all electrons are moving this way. Okay, so we will have a lot of electrons here. So that's what they mean when they say the electrons will accumulate on plate B. Okay, electrons will accumulate on plate B. Okay, and then when the electrons accumulate at plate B, okay, it will cause the electrons in plates A to be repelled. okay, it will repel the electrons in plate A. So for example, we have one electron here. So since this is already negatively charged, so this plate will become negatively charged. So this electron from the A plate will be repelled. So it will flow out again. Okay. So they say the electrons from plate A are repelled. Okay, and it travels to the positive terminal, leaving the positive charge on plate A. Okay, so as it travels, okay, as the electron travels, there are less and less electrons in plate A. So plate A will become positively charged, and there will be more electrons in plate B. So plate B will become negatively charged. Okay, leaving positive charge to plate A. So plate A will become positively charged. Okay, so as the current flows, so it continues. It's a slow process, not a slow process, but it's a process. So it continues slowly. So as the current flow I decreases, okay, so as the current I decreases, the charge Q continues to increase. Okay, so more current flows, but there is more charge will continue to increase. Okay, there will be more charges in the capacitor. And then when there's more charges in the capacitor, the potential difference would also increase. Okay, the potential difference of the capacitor will also increase until a point. Okay, so just now the current would decrease. Okay, the current would decrease as it keeps flowing out. Okay, the current would decrease and the charges actually would increase. Okay, when the charges increase, it will also, the potential difference across it will also increase. So that would be a potential difference increased. Okay, so here would become more negatively charged, here would be more positively charged. That's why the potential difference also increase. And the current will keep decreasing until it reaches a point where the current stops. Okay, the current stops and the current becomes zero, following the voltage would be maximum. Okay, so for example, this circuit has a battery of 12 volt. Okay, so the current will keep decreasing and the voltage will keep decreasing until the capacitor is charged until 12 volts. Okay, so that's what it means when it says, okay, the capacitor equals the voltage supplied by the battery. Okay, the capacitor equals to the voltage supplied by the battery, at which the capacitor has maximum charge Q0. Okay, so the current will keep decreasing and the capacitor will be charged. Okay, it's charging, the capacitor is charging until the capacitor has a potential difference which is equal to the potential difference from the battery. Okay, equals to the voltage supplied from the battery. So for example, we have 12 volt, then the potential difference will also be 12 volt, then the current would stop and the capacitor would be maximum charged. Okay, so this is how the charging process occurs for the resistor. Okay, so you should be able to sketch and explain the graphs. So this is our graph for charging the capacitor. So we have two graphs. The first graph is charge against time. Okay, charge against time. So we know the charges will increase. The capacitor is charging. So when the capacitor is charging, the charges in the capacitor will increase. So it will be an exponential and it will be increasing. Okay, increases exponentially until it reach a value Q0. So this would be the equation for the charge. Okay, where Q0 is the maximum charge, I0 is the maximum current, R is the resistance, and C is the capacitance. Okay, so this is for the first graph. So we know the capacitor is charging, the charge will increase, and we will have an increasing exponential graph for the graph charge against time. Okay, and for the other graph, we have current. We have current against time. Like I said earlier, the current will keep decreasing until it actually reaches zero. So the current actually decreases exponentially with time. Okay, the current decreases exponentially with time. So this would be the equation for current. Okay, so these are the graph for the charging capacitor. We have charge against time graph and current against time graph. For charge against time, since it's charging, the charges increase. For current against time, the current will actually decrease until it stops when the capacitor is reaches a maximum charge, when it's maximally charged. Okay, so this is the graph for charging a capacitor. Okay, for discharging the capacitor, so now we will talk about discharging the capacitor through a resistor. Okay, so the first thing first, for discharging the capacitor, the battery is removed. Okay, so the battery will be removed. Okay, and the charged capacitor, so we will assume the capacitor is already charged since we want to discharge it. Okay, the charged capacitor is allowed to discharge through the resistor. So there is no battery, so this is our circuit. So there's no battery, we only have a capacitor and a resistor. Okay, so when the switch is closed, electrons from plate B begin to flow through resistor R. Okay, so remember how the capacitor is already charged, it's charged with electrons. Okay, it's already charged, so the electrons will flow out from a plate B. Okay, it will flow out from plate B and it will neutralize, it will flow through the whole circuit, and it will flow through the whole circuit and it will neutralize plate A. Okay, neutralizes positive charges at plate A. Okay, so initially the potential difference voltage across the capacitor is maximum voltage. So earlier when the capacitor was fully charged, the capacitor had maximum voltage and also maximum current. Okay, and then it will slowly get discharged, and as it gets discharged, the voltage or the potential difference would decrease, and so would the current. The current will also decrease because the charges are being removed. Okay, so when the charge removed, the current will also decrease. When part of the positive charge on plate A is neutralized, okay, this is where when part of the positive charge on plate A is neutralized, the voltage across the capacitor would reduce. Okay, the voltage or the potential difference across the capacitor would reduce. Okay, this process continues until the current in the resistor is zero. Okay, it continues until the current in the resistor is zero. So when the current in the resistor is already zero, we say that the capacitor is fully neutralized or fully discharged. Everything has been discharged and plate A would be fully neutralized. So now we have equal amounts of positive and negative electrons and positive and negative at both plates, so it's fully neutralized. Okay, and the voltage becomes zero, so the current becomes zero and the voltage becomes zero, and it's fully neutralized. So we say the capacitor is discharged. Okay, so for the graph, it's the same. We still have two graphs. We have charge against time. Okay, and we also have current against time. Okay, like I said earlier, okay, charge would decrease. Okay, charge would decrease exponentially towards zero. Okay, charge decreases exponentially towards zero. So we have this equation. Okay, and the current would also decrease exponentially. Okay, the current will also decrease exponentially towards zero. Okay, decrease exponentially towards zero, and the current is negative because the direction is opposite to that. Okay, the current is negative because its direction is opposite. Okay, so here, so we have this graph for the current versus time resistor, and this would be the equation for the discharging of capacitor, and we know Q naught is maximum charge, I naught is maximum current, R is resistance, and C is capacitors. Okay, so if you want to calculate a charge at a certain point, so we can just put in the maximum, the the R and the C, and we can get the charge at that point. Okay, based on the graph. Alright, so that's for discharging the capacitor. So we've reached the end of 2.2. Alright, thank you. Okay, and this is the 2.3, the final subtopic for chapter 2. Okay, so for this topic, the learning outcome is define dielectric constant. Okay, but before that, what is a dielectric? Okay, so dielectric is an insulating material. Okay, insulating is the insulating material. For example, it can be rubber, plastic, wax paper. Okay, insulating material, therefore it has no free electrons. Okay, it cannot transfer current. It has no free electrons in it. So it's an insulating material. Okay, so dielectric is an insulating material, and that means it has no free electrons. Okay, so when a dielectric is inserted between the plates of a capacitor, so now we have capacitor. A capacitor looks something like this. So the dielectric would be inserted here. Okay, so for example, we have something inserted here, which is the dielectric. Okay, so when that happens, so when we insert the dielectric between the plates of a capacitor, its capacitance increase. Okay, its capacitance increase. Why? I'll explain later. But when we include a dielectric, or we insert a dielectric into the between the plates of a capacitor, the capacitor's capacitance increase. Okay, the capacitance increase by a factor of K or epsilon naught, which is called the dielectric constant or relative permittivity of the material. So that's dielectric. Okay, so this is a dielectric constant. It's a formula for dielectric constant, which is the relative permittivity, and it's defined as the ratio between the permeability of dielectric to the permeability of free space. Okay, so relative permittivity is the ratio between permittivity of a dielectric, okay, so epsilon naught over permittivity of free space, epsilon naught. Okay, so this is relative permittivity. Okay, so this is a capacitor without a dielectric. So when without a dielectric, it would be free space. So permittivity of free space. And if we include a dielectric between the plates of a capacitor, then it would be the same capacitor. It's the same capacitor, but with a dielectric. So this would be permittivity of dielectric. Okay, so relative permittivity is dielectric permittivity divided by permittivity of free space. That means a capacitor on its own without a dielectric in it. Okay, so that's a dielectric constant. Okay, so to calculate, we can also calculate a capacitance of air filled. Okay, air filled, that means without dielectric parallel plate, using this formula. Okay, we can use this formula to calculate the capacitance of an air filled parallel plate. So when it's an air filled parallel plate, we will use epsilon naught here. Okay, and then which is permittivity of free space, because there's nothing in between, so we will use epsilon naught. Okay, so for which is permittivity of free space. So this is another equation to calculate capacitance. And if we have dielectric in between the plates, so this would be our new equation. So this would be the equation if we have a dielectric in between. Okay, so it would actually be permittivity of dielectric. If the earlier one is permittivity of free space. So if there's nothing in between, we use permittivity of free space, and if there's dielectric in between, then we use permittivity of dielectric. Okay, another thing I want to highlight from this equation is, okay, so this is the equation. So based on this equation, we know if we decrease, okay, if we decrease the space between D is actually the distance between the plates, okay. D is the distance between the plates. That means if we decrease the distance between the plates, the capacitance would actually increase. Okay? When we decrease the distance between the plates, the capacitance would actually increase. So I just want to highlight that the distance between the plates is inversely proportional to the capacitance. Okay? Okay, so next we will talk about describing the effect of dielectric of parallel plate of capacitor. So what happens? What happens when we actually insert the dielectric into the capacitor? Okay, in between the capacitor, what happens? So it says here, a dielectric in an electric field becomes polarized. Okay, so it becomes polarized. This allows it to reduce the electric field in the gap. Okay, so what happens is when we insert the dielectric, okay, the dielectric becomes polarized. So it arranges itself like this. So since here is a negative plate, okay, all the positive charge would be arranged facing the negative plate. Okay, and then this side, all the positive, since this is the positive plate, all the negative charges will be arranged facing the positive plate. Alright, so this is what we call being polarized. So it's arranged. Okay, it's arranged. So we say the dielectric in the electric field becomes polarized. So it's been polarized. So when it's being polarized, it produces another electric field. Okay, it produces another electric field. This causes it. Okay, electric field. Okay, so this causes the electric field to decrease. Okay, so this causes the electric field to actually decrease. So when the electric field decrease, so we know based on this equation, V equals to ED. So V equals to ED. So when we insert a dielectric, it becomes polarized. Okay, when it becomes polarized, it has another electric field. Okay, this electric field causes the electric field of the capacitor to decrease. Okay, so the electric field decrease. When the electric field decrease, it will cause the voltage to decrease as well. Okay, it causes the voltage to decrease as well. So what happens to the capacitance? So C equals to Q over V. So now the potential difference also decrease. So when the potential difference decrease, it will cause the capacitance to increase. As I said way earlier, okay, when we include the dielectric into the capacitor, it causes the capacitance to increase. Okay, because V equals to ED. Okay, and since the dielectric is included, it causes the electric field to decrease. So when the electric field decrease, the potential difference will actually decrease as well. And when the potential difference decreases, the capacitance will increase. Okay, so that's how the dielectric affects the capacitance of a capacitor. Okay, and then the final part of this chapter is you should be able to use the dielectric constant. Okay, use the dielectric constant and also use capacitance E equals to epsilon R C naught. Okay, C equals to epsilon R C naught. Okay, how do we get that equation? Okay, how do we get the equation? It starts from this equation. which is the capacitance equation, for the permittability in air. Okay, and then we rearrange it. Okay, we put epsilon naught as the subject. Okay, so we get this is the first equation, and another one, same as the same one as well, capacitance. Okay, so when we rearrange it, we will get the second equation. Okay, so this one is for permittivity of dielectric. Okay, so we have the first equation for without a dielectric, and the second equation with a dielectric. Okay, and then we know epsilon R. Okay, relative permittivity is actually epsilon over epsilon naught. Okay, so what we do is we substitute equation 2 and equation 1. Okay, so this is equation 2 and this is equation 1. So we substitute the value. Okay, and since the distance and the area are constants, okay, it's actually constants, so it will cancel off each other. So therefore, we will get epsilon R equals to C over C naught. When we arrange it, we will get C equals to epsilon R C naught. So this is the equation. Okay, if we continue substituting, since we know C equals to Q over V, so we can continue substituting. So Q over V, and since the charges are constant, so the charge cancel off each other, and we left with V naught over V. Okay, and since V equals to ED, so we can again substitute V equals to ED here, and since the distance are constant, it will cancel off each other and we will get E naught over E. Okay, so this one we are using C equals to Q over V. Okay, and on this one we are using V equals to ED. So if it's a V naught, it will be E naught D. So V equals to ED here, and then D is a constant. The distance between the plates are constant, so we can cancel off and we'll get E naught over E. So finally, we have a few ways to calculate the relative permittivity, which is C over C naught, or we can also use epsilon over epsilon naught, V naught over V, or E naught over E. Okay, so E is the electric field, potential difference, permittivity, and capacitance. Okay, so this is the further explanation. Parallel plate capacitors with no dielectric between the plates resulting in large electric field. Okay, but parallel plates with dielectric reduce between the plates because dielectric materials are polarized, producing an opposing field. Okay, it produces its own electric field, which opposes the original electric field, causes it to decrease. And when the electric field decreases, the potential difference decreases. And when the potential difference decreases, the capacitance increase. Okay, so these are the quantities. Okay, electric field E, potential difference, charge, capacitance, and energy stored. Okay, that's all for this chapter. See you in the next one. Thank you, everyone.